Precision farming is crucial for increasing crop yields while reducing environmental impact. Current agricultural management still relies heavily on human labor and substantial resource input. Recently, micro-air vehicles have emerged as a highly promising solution to automate these tasks. Micro-air vehicles often follow waypoint-based flight paths for agricultural tasks. While effective in well-managed plantations, this approach struggles in complex environments. Trees may deviate from predefined waypoints, and common GPS systems lack the precision needed to ensure accurate coverage of target crops. One solution to this issue is integrating a high-precision RTK GPS system to obtain the exact location of each tree and navigate based on tree coordinates. However, RTK GPS equipment is expensive, and collecting tree data requires significant time and resources. If we only need to collect data for a dozen trees, it wouldn't be difficult. But what if there are 10,000 trees? This would require enormous labor and resources. Additionally, GPS signals can be affected by weather conditions, leading to inaccuracies. Therefore, we propose ForaNav, an insect-inspired online target-oriented navigation system for micro-aerial vehicles in tree plantations. ForaNav requires no prior tree information, enables real-time onboard tree detection during navigation, and updates the flight path based on detection results. It also ensures that the UAV does not miss trees that deviate from planting columns. Moreover, it is deployable on compact, energy-limited platforms. The navigation system consists of 3 modules. The path planning module uses the results from detection modules to update the flight path, and the motion control module utilizes these detection results for vision-based control. To validate the deployment on resource-constrained platforms, we implement the system on an MAV equipped with a Jouvois camera and a Crazifly bolt flight controller. The Jouvois camera is a compact, self-contained module measuring just 1.7 cubic inches and weighing 17 grams. To enable robust detection performance in complex real-world environments, we propose an enhanced histogram of oriented gradients, HOG, based tree detection method, focusing on oil palm trees as the research subject. In the hierarchical structure, the top layer captures the overall structure at a low resolution, while the bottom layer extracts finer details, with the variance of the bottom layer features computed to further distinguish oil palm trees from similar-looking species. Finally, we use the hue and saturation histogram to filter out background objects. This improved detection method supports our navigation strategy, inspired by egocentric visual navigation, for dynamically updating the path. Specifically, egocentric visual navigation relies on local visual cues and a body-centered frame of reference to estimate position and guide movement. Additionally, a view memory mechanism enables recovery from temporary occlusions, ensuring robust trajectory maintenance. As shown in the algorithm 1, our navigation follows these key steps. First, the MAV follows a predefined flight path based on waypoint columns. Second, when a tree is detected, a Kalman filter stabilizes its position for tracking. Third, the MAV continuously adjusts its movement to minimize the offset between the predicted tree position and the image center. Finally, the tree is considered reach the tree once the detection bounding box near the image center. If the MAV drifts too far from the tree, it switches to position-based flight and resumes egocentric visual guidance upon tree redetection. To validate our method, we conducted tree detection experiments using the HOG-based method on oil palm, citrus, and olive trees. The results show that HOG features clearly highlight the distinct shape characteristics of these trees. The high accuracy, precision, and recall of the SVM demonstrate the strong generalizability of the HOG-based method across tree species. We compared our HOG-based method with lightweight deep learning models to evaluate their performance in real-time embedded applications. The results show that our method is more efficient, with lower CPU usage, temperature, and higher FPS, outperforming the deep learning models. In the navigation experiments, we tested 3 maps. Map 1 has 6 trees in a column, with 1 slightly offset. Map 2 has 7 trees on both sides of the column. Map 3, designed for complex environments, has 9 trees across 2 columns, with some clustered together. The navigation framework was first tested on Map 1. The flight trajectories and tree detection results show that the MAV detected trees sequentially. As the MAV detected trees 1 to 6, it adjusted its flight path accordingly. 3 additional flight tests were conducted on Map 2. The trajectory plot shows the MAV detecting and navigating over all trees while updating its flight path. In Test 2, as the MAV approached Tree 3, it bypassed a non-target tree outside the planning column, staying focused on its intended path, as shown in the yellow box. Test 3 highlighted the recovery mechanism, as the MAV quickly recovered from the temporary loss of Tree 6 using stored tree position. Building on these evaluations, Tests 7, 8, and 9 were conducted on a challenging layout with irregularly distributed trees across 2 columns, including several clusters. The trajectory shows that the MAV successfully detected multiple trees simultaneously, accurately distinguishing between them, and correctly updated its path during navigation. This figure shows the MAV's distance deviation from true tree positions across tests, with a mean error below 0.1 meter, outperforming both GPS and RTK GPS, achieved without any predefined tree coordinates. It also plots first detection distances, mostly 0.4 to 0.5 meter, against approach times, 3 to 5 seconds, with online path updates and motion control running in almost equals 0.36 millisecond and almost equals 1.15 millisecond, respectively. In conclusion, this work presented ForaNav, an insect-inspired navigation method for tree plantation management. It combines a real-time tree detection algorithm using enhanced hierarchical HOG and a navigation strategy based on insect foraging behavior. This method can lay the foundation for fully autonomous plantation tasks in precision agriculture.